Now we're going to look at a classical combinatorial problem called the birthday problem that you've probably heard in one form or another, but we'll look at it in the context of analytic combinatorics. So the idea is that you have a group of people, and one by one you ask each member of the group their birth date. And the question is, how many people should you ask, will you ask before you find two that have the same birthday? By the time you get to 365, then you'll have to get, and the next one will have to have the same birthday as someone else, but usually it'll happen much earlier. So the question is, what can we expect on average if, say, the birthdays are random? So a way to look at this as a ball and urn problem is just we've got m urns. In this case, it would be 365 urns, and we ask the birthday, and a person goes into the corresponding urn, and then so each ball goes into a random urn, and then the question is how long until some urn gets two balls. So in this case, the sixth one is where we stop. So if the balls come in random urns, then the question is how long until some urn gets two balls. So let's look at how to analyze that using the symbolic method. So to do that, we'll talk about a birthday sequence. So that's a word where no set has more than one element. So that is each urn has either no elements or just one. And so that's going to be the basis of the analysis. And the first question is, how many different birthday sequences are there? So again, so m is our parameter, that's the number of urns. We want to know the class of birthday sequences, and we'll have a generating function for that class. And again, it's a string that has no duplicate letters, or it's a word where everybody's got either 0 or 1 occurrence. So what's the construction for building birthday sequences? Well, it's pretty simple. We have m urns, we have a sequence of them, and every urn is either empty or has one element. That's the directly construction for birthday sequences. So with the symbolic method, that translates immediately to the generating function for e goes to 1, z goes to z, sequence of m of them just raises that to the nth power. So the EGF equation for birthday sequences is 1 plus z to the m. And then the counting sequence is a coefficient of n factorial in that. So it's, n factorial times coefficient of z to the n in that, which is n factorial times m choose n, which the n factorials cancel, so it's m factorial or m minus n factorial, or the product of m minus 1 down to m minus n plus 1. That's the number of different birthday sequences. So with that, we can use to solve the birthday problem, so with this logic. So we just showed that the number of n character words where no character is repeated is m factorial over m minus n factorial. So again, n's got to be less than m in this, but so that's the number. That's what we just showed. So that's if we divide by m to the n, that's the probability that no character is repeated in a random m word of length n. It's a number that there were none's repeated divided by the total number possible. Or another way to look at that is if we take them one at a time, that's the same as the probability that if we take a sequence of characters, or throw a sequence of balls in the urn, it's the same as the probability that the first time we get a repeat position, it's bigger than n. Because the probability, the first n, that there's no repeat is exactly that. So it's a probability that the first repeat position is bigger than n. So now if we just sum that, we get the expected position of the first repeat. And it only goes up to m because we're going to get a repeat by the time we get to m. So that's a familiar sum. That's the Ramanujan Q function that we looked at in lecture 4, and the result is square root of pi m over 2. Expected position of the first repeat is square root of pi m over 2, and that's the that analysis, it completes the analysis of the birthday problem. So in our original problem, if we had asked people their birthdays, there's 365 days in the year, how many people do you have to ask before finding 2 with the same birthday? Well, you just have to compute square root of pi times 365 over 2, and it's about 24. So in a class of size 24, I've asked people one at a time, a class bigger than 24, you've got a reasonable chance of finding the average number of people you have to ask before finding 2 with the same birthday is 24. There's an analysis in the book that talks about the how many you have to ask to have a 50% chance that you have 2 with the same birthday. It's about in the same range, although that's a different problem. So that's analytic combinatorics with words to take a look at the birthday problem.